In this video, we're going to use Laplace transform to solve a first-order differential equation. The process of Laplace, as a review, is first step, use the Laplace transform table and transform the whole equation from f of t space to f of s space. That's including using the Laplace transform formula for the function and its derivatives. Second step, once you have transformed everything, you want to do some algebra and obtain an expression for f of s. Once you have an expression for f of s, you want to pattern match again on the Laplace transform lookup table from the right side to see what correspond to your expression and therefore look up for what's the f of t, hence solving the differential equation. So firstly, let's transform everything from f of t to f of s. The first derivative of the function, if you look at the formula here, is going to be this part, s f of s minus f0. So I'm just going to copy that down. So I'll use red color for s, so it doesn't look like a 5. So s times f of s minus f0. And the second piece, I want to take away 5. F of t, Laplace transform of that is simply f of s. So that's a number 5 there. So it's and times f of s. That should equal to 9. And Laplace transform of e to the 5t. I want to look at this table, and I can see that the pattern that will match e to the 5t is e to the minus kt. If I want a coefficient to be 5, my k has to be a negative 5, because minus k is going to be then minus 5 becomes positive 5. So if that's my lookup table, I want to write down the Laplace transform of that expression. So 1 over s plus k, but now that our k is minus 5, so that's just going to be 1 over s plus minus 5. In this step, the transform is done. We also want to include the initial condition. Here our initial condition is f of 0 equals 0, so the middle piece is actually going to be gone. Let me just tidy things up a little. I said I want to use a red color for s, so it's different from 5. Okay. Right. Let's just copy the left-hand side. We know that this piece is going to be 0, so that can disappear. So just rewrite the left-hand side with the f of 0 equals 0 substituted in. Number 5, f of s, that equals to 9 times 1 over s minus 5. So second step, I want to obtain an expression for f of s. And you can notice that your f of s is s sets of it minus 5 sets of it. So altogether, you would have s minus 5 sets of f of s, and that equals to 9 times 1 over s minus 5. If I want simply f of s expression, I would divide the bracket of s minus 5 on both sides. So on the left side, once you divide that bracket, it's no longer there. On the right side, you will have 9 times, so copy everything down first, s minus 5, that's a 1 there. When we divide something, that item would actually go onto the denominator. So I would basically have another s minus 5 because I'm dividing that on both sides of the equation. Notice the two brackets are the same, so it's simply going to be something times itself, so it's that item squared. So my final simplified version of the expression is 9 times s minus 5 squared. Okay, so that is a full finished expression of f of s. We've finished our step 2. Now simply step 3, when we have a f of s expression, we're going to come back to the lookup table to find something that looks like 1 over s minus 5 squared. Notice I kept this number 9 in the front as a constant because a Laplace transform is very straightforward when you have linear combinations of it. So any constant can just stay in the front. So my f of t, I know it will equal to 9 times when I transform the rest of the expression back from f of s to f of t. So looking here, the only one with a bracket square is this one. So my expression is 1 over s minus 5 squared. And the formula is s plus k squared. That means my k here must equal to a negative 5. Okay, so with that determined, I can just simply copy down the f of t from lookup table, and the only thing I need to change is k because now I know what my k should be. So t e to the minus k, where k takes on the value of minus 5. So e to the t times e to the minus k and t. Minus and minus makes a plus, so my final answer is 9 times t e to the 5t. And that's this differential equation solved. That's the final answer. So the extra step is if you want to check whether your answer is correct or not. You don't have to do this on the exam, but if you want to make sure you've got time and you want to check, and you can plug in your functional form in the original condition and see if it holds. So in the initial condition, the equation have a first derivative. So that's the first thing I will do. I will calculate the first derivative of this expression. So take a first derivative. I should have a product rule. So 9 times the derivative of this product, which if you remember product rule, I should have u prime v plus u v prime. If my u is t and my v is e to the 5t, my u prime should be 1 times v, so e to the 5t, and plus my u, which is t, times v prime. V prime is take a derivative exponential, which you should have itself. With a chain rule, you have a coefficient of 5 in the front, so 5 there. And that's the first derivative. Now the equation left-hand side, if I plug that first derivative in, I will have 9 e to the 5t plus, this is opening the brackets, so 9 times 5 is going to be 45 t e to the 5t. And I also need to subtract 5 of the function, so minus 5 times the function is 9 sets of this expression, so 5 times that is going to be 45 t e to the 5t. And you notice the second two terms are exactly the same, so they can cancel each other. What I'm left with is simply 9 times e to the 5t. And that's exactly what the right-hand side is going to be. We should also check if the initial condition holds, ft is 0. As you can see that ft here is 9f of 0. When t is 0, 9t times e to the 5t, because t is 0, you're multiplying something by 0, that will be 0. It is confirmed. So these two checking steps has confirmed your expression will satisfy the original equation and the original initial condition. So again, for the last step here, that's an optional step, is for you to check to make sure that your solution is correct. But you don't have to do this if you are confident of all the algebra before you obtained your expression. So the only step you would have needed is up to before this red line. Right, thank you for watching.